How's everybody else day going?
Not bad.
Beautiful morning.
But it is.
So freaking hot though.
Well, not right now.
Not right now, but it's going to be. I meant like the last few days. It's been
Yeah, it's been horrible.
What are you driving?
I have no idea.
I don't see a single car down there that should be modified. It scares me.
All right, I guess we'll get started. So a quick reminder, today is open house.
We'll have barbecuing downstairs.
Oh, I did not know that.
We'll be starting it around
All right, so it sounds like I should try to end lecture a little early or something, send you guys down there.
It is never packed. Nobody needs the stress.
Nobody needs. But yeah, so I'll allow some time, make sure you get your food. And then I will also say if you need to meet with somebody, talk about classes or whatever, feel free to make a little bit of time for that. I know we have lab going on, but, it's okay if you need to go in and out so you can check this out. And again, it's from 10 to 2. And so our lab goes until 3, so I don't want y'all to miss this, of course, especially if there's barbecuing. So yeah, we'll make some time for that. And we are doing 2 labs today. So I do have the papers somewhere. I don't know if they're on my person. Yeah, just one person was out, so I need to find. Yeah, as long as everybody else has their papers too.
Yeah, right, as long as we all have it.
She said 2.
But yeah, I'll find them eventually somewhere in this stack, so. Cool. So yeah, the labs, we'll go over in lab, but it'll probably be a lot of little steps, so that's why I said, a lot of time to go in and out as well if you need to check out the open house or talk to advisors or anything else you might need to get done so you're ready for fall, hopefully. Or transferring, or graduating, whatever y'all are doing. All right, so let's talk about the rest of chapter 7, which goes into phase changes and intermolecular forces. And so this is just reminding us of how things phase change. So again, in a solid, everything is all packed together. And then, we add energy. So we could also say energy, obviously in the form of heat is usually how you do it. So adding heat, and then that starts to move them. But really we want to look at, so what kind of dictates this? And so really we're looking at the intermolecular forces, or we will be. And so in all this, just watch your language. And so what we mean by this is intermolecular, so that's like your interstate highways. So that's between molecules. Because oftentimes as we talk about this subject and talk about breaking these intermolecular forces, students often use the word breaking bonds, and so that would be different, right? So it takes a lot more energy to break bonds. So not talking about breaking bonds, we're just disrupting those intermolecular forces. And so then we continue to increase heat, or, we learned there are other thermodynamic properties that we can change, so change pressure. That could cause the atoms to start moving around more in the gaseous phase, and again, looking at those disruption of intermolecular forces. And so now let's talk, well, what are intermolecular forces? So more broadly, they're just attractive forces that hold matter together in the condensed state. And so like we've mentioned before, so we saw this with the ionic compounds, so those attractive forces were electrostatic. So same thing, we're going to see how we get kind of the different positive, negative, even if it's temporary, we'll look at that. And of course, polarity will come back to haunt us because, right, we've talked about polarity, how that can create a difference in the molecule of a negative and a positive end. So something that's polar, that's also going to influence its intermolecular forces. And so this will dictate the strength of the interactions, and so then that kind of drives why certain substances are solid, liquid, gases. So then we can go back to the periodic table and think about those intermolecular forces. So why is fluorine a gas while iodine is a solid? So those sorts of questions. And so we'll see in our general trend, so the stronger the attractive forces, the higher the boiling point of the liquid and the melting point of the solid. And so we'll look again, we'll dive into the main intermolecular forces and how we can at least kind of guesstimate and arrange and order the boiling points. And so we'll look at how these different attractive forces vary in strength. And again, try to guesstimate and arrange who would have a higher boiling point. And so, of course, the stronger the attractions, the more energy it will take to separate them. So that, of course, again, drives the difference in boiling points, melting points. And then, boiling a liquid requires you to add enough energy to overcome all attractions between the particles. So again, those intermolecular forces. And then just another reminder, so we're not breaking covalent bonds, so we're just breaking those intermolecular forces. And so now let's talk about, well, why are things attracted to each other? So this just goes back to having two things that are differently charged, right? A positive N and negative N. And so we've seen that with our cation and anion, how those structures are attracted to one another because of our positive cation and our negative anion.
I have a question.
Mm-hmm.
Kind of like a long question. I thought it was the intermolecular forces that created bonds. And you said it's not covalent bonds?
So
It would be ionic?
So this is an intramolecular force. Right? And so that's a covalent bond.
So it's like HH intermolecular then?
Yeah, so intra, right? So intra just means it's bonded with itself. If we're talking intermolecular forces, we're talking about HH with HH. So, right, because you have both. So you have the bond, so that would be your intramolecular force. And so in this case, right, a physical bond. And then, so we're getting there, but we'll figure out, well, why these completely nonpolar molecules, though, still have intermolecular forces between them. Does that clarify?
Well, I'm working on it.
Yeah, because remember, this is sharing of electrons, and then this intermolecular force is just the electrostatic potential. So kind of like ionic charges, but except they're going to be weaker, and we're going to talk about that because we'll go into the why and the polarity. And so if you have, in general, a larger charge, that means you have a stronger attraction. And then longer distance is a weaker attraction. And so this is saying intermolecular forces are small relative to the bonding forces. So there's, again, the difference, right? You have your bonding force, your sharing of electrons for a covalent bond, but then you have your between molecule forces that dictate if it's a solid, liquid, gas. All right, so let's start with the weakest of the forces. And this has a couple of names, so if you read it in different textbooks, so they're called dispersion forces or London forces, or really London dispersion forces would be the other name. Or maybe more commonly, again, depending on when you read this, or van der Waals forces. So you may have heard of this by either one of those names. And so the important thing about dispersion forces is, so even though they're the weakest, every single molecule or atom has a dispersion force. So, right, we can look at helium, and we'll look at that, and even those have dispersion forces. And so let's talk about the why. How do we get some electrostatic potential? And so this is a good picture here. So we have a depiction of 3 little helium atoms in a row. All right, let's just say they're all floating around, and the electrons are moving around. And if we could just stop it and take a snapshot, what if at this snapshot, it just so happens the electron density on this one is located on the left here. So that means that we have a partial negative n. So this is more negative, again, temporarily. That means this side's more positive, right? Because the two electrons are hanging out over here. And then what if next to it, its neighbor is also in the same kind of position, again, instantaneously, where you have the electrons hanging out over here. So right here, you have a little attractive force. So then this is your van der Waals force here, right? There's your electrostatic potential, a positive charge next to a negative charge. Again, it's partial, so that's what this symbol means, is partial. So we don't have, right, ions, right, where it's full separation of charges, but it's just at an instant moment of time, we have electron density localized on a certain side of the atom. And then if this happens with its neighbor as well, right, we get a little bit of attractive forces. And so again, this is just, right, an instantaneous dipole. So we take a snapshot, that's how the electrons are, but then they're going to keep moving around, right, and circulating the atom. And so that's why it's just instantaneous. And that's also why it's so weak, right, because it's not like a polar molecule where it's always going to have a greater area of electron density and not. So this just is temporary dipole. So that's important. And so, right, you can imagine helium has a pretty low boiling point, and helium is used, at least historically, it's used to cool down NMR magnets, like really, really cold so that they work. But they've been working to try to convert from helium to nitrogen because of the helium shortages. So that's why it's so cold. And so if we're comparing dispersion forces, your size then matters. And so comparing the trend of the noble gases here, so of course all noble gases are nonpolar. And so the change in polarity, there is none, so that's not a factor. But if we compare the boiling points, so there's helium, so again, that's why it's so desirable, it's so low. And as we increase in size, their boiling point slightly increase. So again, this is in Kelvin, so it's extremely, extremely cold still with a xenon, but we're seeing the trend. And so now we can explain why. So as your molar mass increases, right, you have more electrons, so a larger cloud, and so this cloud can be more polarizable, and your strength increases. And of course, again, the stronger the attractive forces, the higher the boiling point. So again, you see that in that trend there. So shape also matters. So you want to have good contact, right? A lot of surface area. And we can think about this. This is a good depiction here, but we can kind of draw it, right? Kind of give it a representation. So there's pentane, and then these hydrocarbons can kind of stack like that. So they stack really nicely. And so this is also how you get saturated fats eventually, right? Those chains are long enough, and they all stack super nicely, so that gives them a pretty high boiling point. And comparatively, so if we compare it to neopentane, where it's got this tetrahedral structure, right, that's a lot less surface area for interaction. So just trying to compare. And so because of that, so now looking at the boiling point, so again, pentane and neopentane, notice that they're just isomers, so they have the same formula, right, same molar mass. So they're all C5H12. But our pentane has a slightly higher boiling point of 36 degrees Celsius versus neopentane that's 9.5. So this would be starting to boil right at room temperature. That would be kind of a pain to work with, versus pentane, which still would have a pretty high vapor pressure at 36, but you can pour it. All right, so now we're just comparing our N-alkanes, and so seeing this trend, and again, it's increasing with increasing molar mass, and N-alkanes just refers to a straight chain. So these are all straight chain alkanes, so no branching. So again, they're all going to be stacking really nicely on top of one another, and you can see their boiling points increase. And so if we were to compare branch chains, we would expect a lower boiling point since, again, there's less surface area between them. So the next type of intermolecular force is these dipole-dipole interactions. And so now these polar molecules come back to haunt us. So now we kind of know why it's important to identify what's a polar molecule, what's not. It's so we can also estimate the strength of their boiling points and their interactions. And so unlike our nonpolar compounds where we have to depend on the electrons circulating around to create a temporary dipole, right? Polar molecules have a permanent dipole. And we can, kind of remind ourselves of different polar molecules. So usually some sort of carbonyl or CO. And of course, right, we've touched on this in our previous chapters. I know we're going fast in the summer pace, but you've at least hopefully gotten a taste of, figuring out the polarity and looking at y'all's labs and grading them. I think everyone did a pretty good job on this, actually. Figuring out the geometry, do the charges balance out or not, and then figuring out polarity. So I think you guys have a grasp on that, so I feel pretty good about this class being able to do that. And so right once you identify a polar molecule, then you know that it's going to have this intermolecular force, again known as our dipole moment. And so now we're just kind of comparing some structures here. So we have, I believe this is acetone. And of course, if they line up like that, so better picture with our electrostatic potential. And our red reminding us that, of course, our oxygen, not only is it electronegative, but it has those two lone pairs, which they do not draw in, but we can add those in, right? Just thinking about those electrons, so they're negative. So that's, again, leading to our large polarity. And, of course, there's our intermolecular force, or our electrostatic potential interaction there.
So if you have something like methane, like CH4, that is like two polar, does it not have a very strong dipole?
Yeah, well, you said nonpolar, right?
Yeah, it is, sorry.
Yeah, exactly. So it's methane, you expect, and that's why it's a gas. So now you've answered, well, why is methane a gas? It's because it's, yeah, so you can look at, so let's stop and analyze. If we compare methane, I'm trying to think of other substances that are polar right now. But let's just compare like methane versus methanol. Methanol's too much. I guess let's look at acetone. What? Ethanol is also hydrogen bonding, so that's why I'm avoiding it. But yeah, let's just compare it to acetone since I'm uncreative this morning. But yeah, comparing, methane. So of course, not only is it light, but we have very little surface area as well for methane to interact with itself. It's nonpolar, so it's not going to have, right, a dipole moment. And so this would be something you might do in an exam, so we can identify, okay, methane, nonpolar, you want to say what intermolecular forces it has. So I'll call them van der Waals, but again, London dispersion, dispersion, all used interchangeably. And then, so we would expect it to have a pretty low boiling point. And I don't know methane off the top of my head. I do know it's a gas, though, so we all know it's a gas. Let's ask Wikipedia. Again, only good for science, really. Don't look up history or current events. So methane, where's our... Yeah, so really cold. So that's the melting point and the boiling point, so right, very cold. And if we compare that, so the other thing you'd want to compare for an exam is kind of like their mass. So ideally, we'd want to compare with something with the light molar mass. And so let's write this as well. So 16 grams per mole. I took some liberties with rounding. But, right, fairly lightweight molecule as well. So thinking back to those noble gases, how they increase as they got heavier. So same thing with our molecules. And so acetone, I think we all know, is at least a liquid. And let's remind ourselves. And so that's, let's look at so the boiling point is 56 degrees Celsius, so a lot higher. I was a little unfair because it is heavier. I'm trying to think of another molecule right now. It's not a gas and not a hydrogen bond. But I can't think of a good comparison right now. Maybe it'll come to me later. But let's keep, so we'll write that just for reference. So 56 degrees Celsius, it was a little larger, so not the greatest comparison, but it does have, again, our dipole. And so don't forget, that's the other thing, right? So these, of course, it's dominated by the dipole forces, but it still has London dispersion, van der Waals forces. So everything has van der Waals all the time. It's just each molecular force gets stronger, so the van der Waals become essentially negligible. And so just comparing, so maybe this would have been a somewhat decent comparison for our polar and non-polar. So they have here formaldehyde versus ethane, and so this is a better comparison than our methane, since at least these are the same mass or pretty close. And of course, not the same formula. And formaldehyde, so this is, right, our smallest carbonyl molecule. And so again, it's going to be polar with our oxygen. And so its boiling point is -19. And comparing that with ethane, which is -88. So you can see the influence, right, of our dipole-dipole force. Since they should have about the same van der Waals with the molar mass, you know, you could argue even ethane might have a little bit stronger van der Waals because of stacking versus the formaldehyde. But again, the dipole is stronger and dominates that. And so as you might imagine, as things get more polar, and this is where, you know, you could ask the internet for the dipole moments to, again, kind of give you a sense of things. And so we're seeing propane, which pretty much has a negligible dipole moment, which we would expect, right? Propane is just our straight chain alkane. I can zoom in on that if we can't see. And if you want me to draw these out more explicitly, I can. But right, this is just C3, H8. So no, really, we expect it to be nonpolar by our classification. Then going up to ether. So now we have a little bit of polarity in the middle, from that oxygen, but from our dipole moment, right, not too extreme. You can kind of tell that from the shape, but notice, right, increasing boiling point slightly. Then ethylene oxide, so this is one of the few, not one of the few, but one of the first examples we've seen in this weird epoxide group, so makes a little triangle. So normally I don't try to throw epoxides at you, otherwise you won't know how they connect. But given this geometry, right, it gives it a little bit more polarity. And so again, that's reflected in the dipole moment there. And then acetaldehyde, now it's kind of on one side of the molecule, making it more polar. And again, increasing boiling point. And then acetonitrile, so that's a lot more polar, right, with our nitrogen on the end there. And it has comparatively the highest boiling point. And then again, our van der Waals are essentially the same, since they all have about the same molecular weight, and they're all pretty small, so not too different in geometry. So again, mainly the difference in dipole that's dominating this difference in boiling point. And acetonitrile, dipole moment of 3.92. Any questions about?
Just to make sure I'm getting it right, so van der Waal is size, or weight and shape,
Yeah,
and dipole is the polarity.
yeah.
Okay. Just wanted to make sure I was on the right track.
And then, so our last intermolecular force, last and certainly not least, it's the strongest. And so you would probably want to write this down so you remember it. And so this is a very special situation. So basically it happens when we have a dipole moment that becomes extremely polarized. And we might have mentioned this before, but it's when we have a very electronegative atom bonded to hydrogen. And so we've mentioned, right, hydrogen only had one little electron to begin with. So if something is really electronegative, it's almost going to strip that hydrogen, essentially making it just almost H+. And this creates, right, a very strong then electrostatic potential. But it only happens when hydrogen is bonded to oxygen, nitrogen, and fluorine. So I would write that down. So it's only with those. So oxygen, nitrogen, fluorine. So with those three, then we say that's a hydrogen bonding. So anytime you see that. And so this is why, you know, a lot of alcohols then have a high boiling point. So they all have the OH. And I'm sure ammonia, relatively speaking, also has a high boiling point. Same with HF. And like we mentioned again, so hydrogen has no other electrons. And so when the electron is pulled away, it becomes de-shielded. So again, it's almost essentially giving you a naked proton there. So that's where, again, your strength comes from. And so our exposed proton acts as a very strong center of positive charge, which attracts your electron clouds from your neighboring molecules. And so you can also compare this by how many hydrogen bonds. So this is, let's see, this is good old ethanol here. So the tasty alcohol. And so again, you have one OH, so you have a hydrogen bond. Let's see. Oh.
So if that's the case, why is like, I guess water, H2O, has a pretty high boiling point, doesn't it, technically, compared to everything else?
Yeah, so that's, you're getting to one of the beautiful things about water. So water, right, has two hydrogen bonds then, so that's kind of why it has an advantage over ethanols, one. So this is another way to kind of rank them, right, count up, well, how many hydrogen bonds do we have in a molecule? So two hydrogen bonds. So yes, water is extremely unusual because, again, that low molecular weight of 18 grams per mole versus what's ethanols? Anybody want to add that up? 2 carbons, an oxygen, 6 hydrogens.
46.
Sounds about right. So 46 grams per mole, right? So this is almost 2, or greater than 2, almost 3 times higher. But, like you all know, so water's boiling point is 100 degrees Celsius versus ethanol's, which is, I'm going to say 78, but let's look that up. Yeah, 78.
So is that why you were saying a lot of it is guessing, because there's so many factors that go into it that you're basically using as much of the information you can to guess their boiling points over each other?
Yeah, or like, it's kind of like on an exam, right? I can only ask so many, I can compare alkanes, I can compare surface areas, right? But I can't give you too many variables, because then, yeah, you won't know, well, how does the mass affect it versus like a dipole. So like I couldn't give you something that's nonpolar and huge versus something that's small and a dipole, because then you're like, well, I'm not sure without a reference. Yeah, but I could ask you, comparatively, like these are increasing in polarity, or maybe like you try to rank them on polarity, that sort of, that's how it would be on an exam. Or so again, hydrogen bonds are very strong, and substances that can form hydrogen bonds will have higher boiling points and melting points than substances that cannot. So again, we saw that with water, and so we'll see that again here. So they're comparing ethanol and a dimethyl ether. So again, these are isomers, so they have the same molecular mass, so that's not driving the difference. But we see, right, ethanol, again, a lot higher at 78 versus dimethyl ether of -22. So that's really showing the power of the hydrogen bond. And don't forget, so write out your molecular forces. So what does dimethyl ether have? What intermolecular forces?
Positive.
So yeah, not one of our choices. So we have van der Waals forces, we have dipole,
Oh, okay.
hydrogen bonding.
I thought you meant like the force on the periodic table.
Oh,
But you're talking about like the dipolar and stuff like that?
yeah.
Okay.
So does it have van der Waals forces? Yeah, so they all do. So we know that's there. And does it have dipole? I see like a kind of slow nod over there. So yes, right? So it's small. So I think if we remember back from our other graph, and we could even note that it's got a small dipole. It's not crazy polar, but it does have an oxygen in the center. Versus the ethanol. So what does ethanol have? So van der Waals. Does it have dipole? So is it polar? So I see a nod. So it still has dipole. And then what else does it have? So it was the one we just learned. Hydrogen bonding, right? Because there you see it. Oh, there's my oxygen bonded to the hydrogen, right? Compare that with the ether. And it's kind of hard to tell, I'll admit, with this space-filling model, but if you can tell, right, your oxygen is next to your carbon, and there's no hydrogens on there, so we don't have any hydrogen bonding.
So it's just a direct bond between the oxygen.
Yeah, so it's either, right, again, oxygen to hydrogen, or nitrogen to hydrogen, or fluorine and hydrogen. So just those 3 elements, yes, and anytime you see a hydrogen on one of those, you got to think, boom, hydrogen bonding. And so let's not forget to add that. And so that's where you go, okay, van der Waals are probably about the same. Dipole, you could argue ethanol maybe has a slightly stronger dipole, but that wouldn't drive that much of a difference between them. It's really the strength of the hydrogen bond, which I think is pretty fascinating. And this is again a reminder that we're not breaking any chemical bonds though. So even though these hydrogen bonds are really powerful and do beautiful things for water, it's still only 2 to 5% the strength of a covalent bond. And so this could also be a good chart to examine on a graph on an exam. And so like some sort of exam question would be, what explains this anomalous behavior of H2O with having such a high boiling point? And of course, this is again just showing hydrogen bonding. And so comparing, your group 4 and group 6 compounds with no hydrogen bonds, so they just kind of follow that molecular mass trend for the most part, which we expect, right? They're all pretty small, they're all nonpolar, so just increasing mass is driving this. And then again, our anomaly of water is super high, comparatively speaking, again, for its molecular weight, right? It should be like down here if there was no hydrogen bonding, but instead it's anomalous and does not follow our trend. And ammonia is not on this graph, but that could also be on there, or HF. The ammonia's boiling point, it's not like that high. So it's still negative 33, but I'm kind of curious why that is. Maybe it's just not as strong. And so let's look at other properties that the intermolecular forces dictate. And so if we can identify our intermolecular forces, then we should be able to determine all of this. And some of this you may have done before. If we get bored in lab, we can certainly do this demo. And so you probably are familiar with surface tension. So we see it a lot with water all the time, how it beads up everywhere. Capillary action is related, but I think we talk about capillary action. Oh, I guess we don't talk about capillary action. Capillary action is somewhat related to surface tension. It just kind of depends as well how well the molecules can adhere to the sides and kind of climb up the walls. So surface tension is related, but not the same. And so this is just a property of liquids that results from the tendency of liquids to try to minimize their surface area. And so what this means, and where you probably have seen it, and if you haven't, like I said, we should do it in lab. And so let's just look at these two molecules. So they're comparing, we wouldn't want to use this, but we would use another alkane. So water, and so right, we already know water has van der Waals, dipole, and H bonding. Versus, so does anybody recognize this? I don't expect you to, but. So this is benzene, C6H6. We've talked about it briefly, but here it is again. So remember, it's this ring structure. Each of these represents a carbon. Don't forget that every carbon needs 4 bonds, so all of these have a hydrogen coming off of this. But benzene is a planar molecule, so you have to remember that as well. It is a little funny, so it is more polar than you expect because it has this weird ring, and so this aromatic ring kind of makes it bond with itself, but it doesn't have hydrogen bonding. And this happens with other alkanes as well. And so why I said we wouldn't use benzene in lab. So have people heard of benzene before? Somewhat. So it's carcinogenic, so that's the biggest problem, obviously. But just a fun fact. So back in the day, before they knew it was carcinogenic, organic chemists especially, you know, at the end of the day, playing with your chemicals and probably not wearing gloves back in the day, you'd want to wash your hands properly. And so they thought properly, you know, you got to get off the organic, so they would do a benzene dip. Like literally, you know, benzene dip with your hands. So I think they got cancer over time. And obviously we don't do the benzene dip anymore. And well, anyways, we won't go down the rabbit hole of trying to phase out different solvents, but the deuterated version is still commonly used as like an NMR solvent. But anyways, the point is, so we have van der Waals. I have a little bit of dipole. But we have no H bonding. And so this means, have you ever done this where you try to see how much water you can get on a penny, like how many drops of water? And then have you ever compared it to like an organic, like ideally heptane would be okay. Well, anyways, we should maybe try this in lab if you're bored. Because with water, right, it'll bead up since it has a very high surface tension, so it kind of makes that little bead, right? And we've all done that. We poured water too high and it kind of beads up. It sticks together, right? High cohesion with those intermolecular forces. But any organic like benzene, or again, if we were to do this in lab, we'd probably use heptane or pentane. You do not want to use hexane. So this is another warning. So hexane is toxic. So hexane is used a lot, especially like in industry, and people use it like to clean up oil spills pretty willy-nilly. But what's problem with hexane, so hexane itself is not toxic, but when you breathe it in and then it gets metabolized by your body, it's a 6-membered chain, and so I have to look up exactly, I forgot what your metabolic byproduct is, but it's the correct length to mess up your synapses. So if you get overexposed over time, you know, this is like long-term exposure, you could have like motor control issues and issues with, you know, other functioning. So I always tell people, you know, try to avoid hexanes, because like I said, I've seen people just like pour it all over the ground to clean up an oil spill. It's really good for cleaning up oil spills, but should not use it. So heptane, this is of course the 7-membered ring, or 7-membered chain. So this is fine because it's not 6. So this is, it's only because it's 6 carbons that it's either the wrong or the right length, depending how you think about it for your synapses. So it's the appropriate length to mess it up versus either the longer or the shorter version, so they don't have any of those issues. So you'd want to use those for safety, but again, you try to put a lot of hydrocarbons on and they'll probably just spill over a lot faster. So if we get bored, we can definitely do this in lab.
Whoever has to deal with that, kitty litter and gasoline.
What? Kitty litter and gasoline?
Kitty litter, soak it up, you use gasoline at the very end, you light it on fire, it burns up all the oil that's left.
What is that? That's got to be toxic, right? Cat litter always smells bad.
Only like, you know, same stuff that comes out of your car. I just do recommend leaving your garage open for it.
Yeah. So then, like we're seeing with our surface tension, so the stronger our intermolecular forces, the higher the surface tension. And if you were to raise the temperature of your liquid, it does reduce the surface tension. This can also be kind of related to viscosity. maybe I shouldn't bring up viscosity. And so this is kind of a recap. So like we saw, if we raise the temperature of a liquid or anything, that increases our kinetic energy. And then of course that increased molecular motion just means you have more flexibility in stretching the surface. And so surface tension is pretty similar. And so this allows us, or this is basically the phenomenon then of why can you float something like a paperclip that might be technically less dense than water. And so all of that is, again, there's cohesive forces of your molecule and how that keeps the surface. And this is also how like bugs can walk on water. And so again, the same thing. So greater your intermolecular forces, especially water, right, your greater your surface tension. So that's something else that you could experiment with different liquids, right? Can you float a paperclip in different liquids with the surface tension? Or does it only work with water? You know, does it work with ethanol with only one hydrogen bonding? So different experiments you could try.
So theoretically, if you wanted to walk on water, you would have to have less density than the water.
Yeah, that too, but then also, like, could you spread out yourselves? Like, could you be like a bug? Because, right, you don't have to necessarily be less dense, just could you spread yourself out and then such that those cohesive forces would keep you up? Yeah.
I think that's called a belly flop.
Has anyone floated, though, directly after a belly flop?
It feels like you do for a second.
Yeah, so there's a balance, right, of your body trying to, the poor water and the cohesive forces trying to keep you up. Yeah. So now I want to see some walking on water too. Like maybe we get some sort of bug-like stilts, you know? I don't know how you could do that.
Reminds me of snowshoes.
Yeah, exactly. We need snowshoes, but water shoes.
You watch Mythbusters a lot? You know they have a whole episode on that.
Really? I didn't.
Yeah, they have a whole episode of trying to walk on water, creating like stuff. So there's 3 creatures in like nature that actually can walk on water. The Jesus lizard.
Yeah, I was like, what are we talking about?
No, there's an actual.
We're all gonna Google Jesus lizard.
No, I'm serious. So it's what it does is it has like wide paws and it can actually run so fast and it uses its tail to balance and steer itself on the water that it can actually run across the water. Yeah, and they actually create contraptions and stuff.
There, I had to find him. So
The
did
Jesus, I'm not like messing with y'all. But yeah, they can actually straight up run across
Oh,
the
it's
water.
those guys.
Yeah. Oh God, yeah. So Jamie and Adam both sat there and tried to make contraptions that they could use to run across the water.
So
And
did
then
it
they used
work
an
ever?
Yeah, and then they used an Olympic sprinter to try out their contraptions because they couldn't run fast enough.
Imagine the horror of seeing someone on all fours just running across the water.
Well,
No.
they only use 2 legs, so the Jesus lizard actually stands up on its back legs and runs across.
Oh, that's
That's
fascinating.
If you look at its tail, how it has that little fin, it actually drags its tail in the water and uses its tail to steer itself while it just runs straight, but the tail will actually steer it.
Now I feel like we need to watch a YouTube video.
Imagine a fully grown man just running across the water.
Watch that episode, they legit try, and it is hilarious.
Oh, there it is. Ripping out water.
Oh my gosh, this is.
Here it goes. I talk to my plants like they're babies.
Hey, you don't need to get that personal to get the State
Ads.
Farm personal price plan. It just helps you create an affordable price. Like a good neighbor, State Farm is there. Call or click to get a quote today.
Passed on the mail.
Some young Costa Rican basilisk lizards are looking for food. Basilisks have been nicknamed the Jesus Christ lizard. Why? This adult male, probably the father of the young lizards, can't tell us. Nor can this female, exclusive property of the territorial male. It has nothing to do with the feeding habits of the basilisk, which consists primarily of insects and berries.
Okay, berries.
As it stalks the young basilisk.
Oh man.
The basilisk is called the Jesus Christ lizard because it can walk, well, really run on water. It bicycles its hind legs.
But it's like, they run just like that, something like that. Someone was buying trend back in the day.
Pretty funny.
Those are all together. Anyways, sorry.
I mean, yeah, surface tension in action, though. So that's how it can run across. So I guess they were unsuccessful, is what you're telling me in the Mythbusters?
Absolutely 100%.
Like, I was just like, what? How many layers of surface area? Like, could you spread yourself out?
The basilisk lizard has so much going for it. So it has micro-density bone structure. It's super light.
Okay.
It has span foot. So if you look at it, it has webbed feet on the backside. And when it runs, the reason it runs like that is because it literally slaps the water, does like a quick turn, and then instantly comes up. So it's using surface tension. It just basically just slap the water real quick. And if you watch them in real speed, they're like,
So you're telling me we need to create a genetic abomination between a human and a Jesus Christ lizard.
yes.
Probably wouldn't for, that's where you need to take bioethics, like engineering. All that gets pretty interesting, though.
A handful of war crimes and violating the community. Another handful of ways, but it's okay.
I mean, there's already a bunch of apparently bioweapons labs that are being funded everywhere, but
Geneva suggestion.
anyways, back to vapor pressure though. So vapor pressure, so this again follows along with all the trends that we've been saying. And so vapor pressure is just the pressure exerted by vapor when it's in dynamic equilibrium with its liquid. And so all that's kind of saying is we have some liquid here, and let's just start with water for a second. And so there's some sort of equilibrium with the environment. And so, right, even though it looks like it's just a cup of water, there may be H2O molecules flying out of there. And so that's where the pressure comes in. So with water, you probably don't notice it, but I would say you would notice this. Yeah, that's part of it, like the rate of evaporation would then be directly related to the vapor pressure, because then if something has a low vapor pressure, then it's evaporating. Or, sorry, high vapor pressure, so it's high meaning, right, you feel it. And so with something that would have a high vapor pressure, I don't know if any of y'all have ever worked with like ethers before, like diethyl ether. But you can still feel it with like ethanol. So if you've ever had ethanol, right, you kind of breathe it in, like especially if you're going for that shot, right, and you can smell it, right? Maybe we're not alcohol drinkers in here.
I can't legally answer that.
I can't. I was trying to get some sort of vapor pressure. Everyone's just blank. All right, I was going for the two possibilities: ether, ethanol. But right, the point is, like, it almost feels like you get hit in the face with the liquid, right? Especially, like, opening up a can of ether on like a hot day, especially. So right, diethyl ether has a pretty low boiling point. And this, you know, we used to get drums of ether shipped in. It's summertime. You open it up, and it's, you know, it's like you're smacked in the face, and it's just because of that vapor pressure.
Could the same thing be like applied to like bleach when you open a fresh using a bleach up and hits you right in the face? Not as strongly, but.
Yeah, I mean, that's going to be a part of it because that's why the molecules are coming out, right? Because there's some sort of equilibrium, but then, of course, your nose is extra sensitive to that bleach smell. So that's why you right, the vapor pressure is why it's coming out, but then the bleach itself is pretty triggering, so.
It's even worse if you had pneumonia.
Yeah, I've accidentally gotten ammonia in my face. I was doing a leak check, it was
Oh,
leaking.
no.
At least it wasn't too much, though. And so the weaker the attractive forces, so, right, that's why I brought up ether and ethanol, because those have weaker attractive forces than water. The more molecules will be in vapor, so the weaker the attractive forces, the higher the vapor pressure. And so, right, that means the more volatile the liquid, and like you mentioned, evaporation can be related then.
I have a question regarding vapor pressure. So like, okay, it's hard to explain this, but so my old jobs, we had this one like grease stripper thing, whatever it's called, grease cleaner, I don't know. But when you spray it and when you breathe it in, it feels like something's being stripped off of your lungs. Like it is such a really not great feeling. Would that count as vapor pressure or not? Or because like when you inhale it, it like I can't describe it, but it smells and feels cold when you inhale it, and that's when you feel like basically your lungs being stripped up, being like stripped. Something's being stripped from your lungs. I don't know what it is, but if you feel that.
That's
I don't know
probably,
what that is.
I'm assuming, yeah, because it sounds like if it feels kind of cold, there's like some evaporative cooling effect, so that would be related to vapor pressure, like if it's that volatile that it's evaporating.
It'll take me a while if I can find you the bottle of it.
Yeah, I am kind of curious now.
Because, yeah, I'm hoping it has no lasting effects. I inhaled way too much of that.
Yeah, there's so
That's a
many
lot.
different degreasers and stuff out there.
Oh yeah, this was called degreaser. Yeah, it worked great, but it sucked, just health-wise.
Yeah, and you do have to be careful, and I think everybody kind of knows, right? That's why you're not supposed to mix acid and base cleaners at home, right? You don't want to mix your HCl with your bleach, because you can literally die. Like people have died from accidentally doing that. You release chlorine gas, and if you stay there, you just get overwhelmed and pass out. So. Vapor is dangerous. Like even like people also don't realize, like even if you just want to have like a liquid nitrogen tank or like dry ice.
Casually in your room, in the corner.
Yeah. If you want to have it casually in your room, you have to think about ventilation, because even like CO2, right? Over time, it's going to eventually fill up your room with CO2, and so you don't want to be like overwhelmed. So that's like a safety thing. Like if you're ever filling up like liquid nitrogen, you can't be in a closed room, because what if, something happens and you pass out and then it's filled with just nitrogen and then obviously you'll die.
Is the reason why like you have to have a really well-ventilated area when you're creating soap, is that the same reason? Because like the chemicals used, like the lye and stuff like that?
Yeah, except it's more like because it feels caustic, so that's because it's strong bases.
Oh, okay.
Yeah, I haven't heard of anyone being overtaken by like base fumes necessarily, but it would be kind of irritating. And so now we're just relating vapor pressure versus temperature, but there's some things that we want to note on this graph. And so we have it labeled here. And so notice this is in torr, and this is 760 torr. So that corresponds to 1 ATM. And so first we can note the general trend. So obviously as we increase temperature, right, that's going to cause more molecules to escape and enter the gaseous phase, thus increasing vapor pressure. But once that vapor pressure gets to 1 ATM, right, that's what we dictate as normal boiling point. And so all that's shown here, right, again, so you could look at the vapor pressure of water at a given temperature, and then it's just going to increase until you're at your boiling point. And that's when, again, your vapor pressure is at 1 ATM, and that temperature is what dictates the boiling point. Does that make sense, what this graph is showing?
So is your boiling point your rolling boil? Like the most it will be able to boil, or is it like as soon as it starts to boil?
I would honestly have to look at when it's defined, but it's probably like when it starts. But it's gonna be whenever the pressure is at, so you would have to like measure the vapor pressure technically to
Just
give the
come
best.
over your kitchen to measure the pressure.
Yeah.
Just come in hazmat suits with a little temperature.
Yeah, because it would probably get pretty close as you start getting towards the boil, but
This is not like a stupid question, but is there any chemicals that you should absolutely not, under no circumstances, boil? Like, top of the list.
You have to think about it.
I'm at the top of the top, like, there's, okay, you shouldn't do this, and this one's like, dear God, do not do this, not touch it.
Gasoline.
That works.
well, you could boil gas. This sounds smart.
You can boil it once.
I mean, it depends. Is it a closed system of gasoline? Like, I heard of some engineers trying to make some sort of weird convection thing from ammonia, but like, as long as it was enclosed, it didn't really
No,
matter
I mean,
too much.
like, a full-on big, like, big soup-style pot with a big lid on it.
I don't think you should be boiling any chemicals in your kitchen.
And,
Okay, fine, a friend's kitchen.
well, I guess the other problem with boiling is, like, not to mention just things combusting and reacting, is like, if you heat something, it's gonna expand and do a phase change. So, right, you could take carbon dioxide, and that would be an explosive bomb in your kitchen if you heat it up, right? Because it started as a solid, goes to a gas. You could quantify that, right? We could do the math, figure out how much a gram or whatever CO2, how much gas that's gonna make. So there's your explosion right there if it's a closed system, so.
How to renovate your entire kitchen in less
Then
an
do
hour.
it in your enemy's kitchen.
Just in front of your enemy, like, what are you making? Oh, I'm making CO2. What?
I think at that point it'd probably be easier to just leave their stove on without the fire going.
Oh yeah, exactly.
Yeah,
Probably. They slide a match and the whole thing. That's why you don't smoke in apartments, kids.
yeah. You could also ask somebody who makes meth how to cause an explosion. So now let's look at how to quantify this. So now we're actually going to quantify this, so the energetics of melting. And so blah, blah, blah. And so this makes sense. So if we're trying to melt something, so anytime, right, we're heating something up, we're adding heat, that's going to be an endothermic process. And then if we're trying to go the reverse, then anything going the reverse, so, you know, gas condensing back down, and then that liquid freezing, so all of those are going to be exothermic processes. So they have to give heat to something. And so again, melting requires input of energy to overcome the attraction. So again, intermolecular forces, not intra. And so now we get to go through the heating curve. And so just ask questions. And so really the tricky part of this is the units. And I will say, right, units can change around, especially if you go look at other reference tables. And so let's first break down what this is. And so as we heat a solid, the temperature increases until it reaches its melting point. And so that means we're kind of here in this curve, it's saying. And so if we want to quantify how much energy it takes to reach this melting point, it's given by this general formula. So Q just represents heat. So how much heat, right? And this is going to be energy, usually joules. And so again, why I say usually joules is you have to pay attention to your units. And so we can look up the specific heat of a substance based upon its state of matter. And so it'd be the mass of that substance times your heat capacity here. So this is heat capacity. And then times the change in temperature. And so we should maybe look up another table too. this, I was trying to find, oh, that was not useful. I was trying to find a nice chart. This is kind of excessive. So this one is giving specific heats for water at different temperatures even, but just trying to get you to see, right, they could be in different units. So you just always have to be aware this is. All right, I'll look around for better charts so we can kind of see, because you could be given this in moles as well. So even though this formula is mass, right, they could give heat capacity in moles. It could be in different units, so you do have to watch your units there. And then once all the solid has been turned into liquid, so we'll have to figure out how to do the state change, then the temperature can rise again. And again, you would have to look at the heat capacity, since water does vary a little bit in terms of the different states. All right, probably in my notes, internet is not being as useful. And so the heat of fusion then is how we quantify how much energy is required to melt, so do our state change. And we have both, right, the heat of fusion, so fusion is when we're melting. And so, right, melting is going to be in the forward direction, adding heat, and then freezing is going to be in the reverse direction, right, losing heat, but the energy would be the same. And so again, melting is always endothermic, so adding heat, so it's positive. This is showing, again, how much energy you add in to melt it. You have to lose that energy to recrystallize. And so as we see, right, our fusion, our melting energy is generally less than our vaporization. So that means, right, our vaporization is energy needed to go from liquid to gas, at least in the forward direction. It would be how much energy we need to condense. And these are just rough values. And so on an exam, I'd probably have to give you some values. I would not expect you to look them up, but just be prepared to plug them in with however I give them to you. So in moles and grams. So those units can vary. And then if you're given a sublimation question, so the sublimation, the energy needed to sublimate. So sublimate, right, is solid to gas. Then you just add the two values together. All right, so let's try to go through. So we're going to go through this entire segment then. And so let's see. So the question could be on an exam, how do we take our ice? So we're starting at ice at negative 25 degrees Celsius, and I want to heat it up all the way to, I think, 125. And let's see, we have 1 mole amount. And so we'll go through the math. And so step 1, and so I'm zooming in and out here. So step 1 of this curve, so notice, right, if you were to do this on an exam, you want to break down every step because you have to do everything kind of separately. And again, depending how far you go on the exam. And so our first leg is we want to just heat the ice from negative 25 degrees Celsius to the melting point. And again, that's dictated by this formula. So your hint, if ever you're getting confused, well here, right, notice we have a change in temperature on that leg, so we need a formula with a change in temperature. And again, we can get this formula usually given in mass, like I said, could be given in molar amounts as well, just depending. And then notice that we have to find the heat capacity for ice, and so it is a little lower than water, and again, this would be provided. So the heat capacity for ice is 2.09 joules per gram per degree Celsius. So right, notice units, so make sure everything cancels out. And I'm just going to rewrite their work. So mass, right, convert this to mass, so we have 18 grams of it, times our specific heat. So again, look at those units that you're given and make sure that they do indeed all cancel out. And then so times, so right, we have degrees Celsius, so we need to multiply by T. And then our change in temperature, of course, is 25. So just the difference. And then let me plug in my calculator so you can see the work here. And so again, watch your units. So we're in joules. We'll verify, right, everything cancels, grams, grams, Celsius, Celsius, leaving us with joules. So 18 times 2.09 times 25. And so that gives us 940.5 joules, so just what they wrote here as well. And so they rounded to 3 sig figs from our 3 sig figs, of course. And so now segment 2. This is pretty, again, it's kind of self-explanatory, but it depends, again, on your heat of fusion. So it depends on how they give it to you. So they could give it to you in kilojoules per mole, but, you know, they could also give it to you in another energy per gram or something. So just always watch out. And so in this case, we don't have to do too much converting. So just follow along with our units. And so we just have to multiply our heat of fusion by our number of moles. Again, watching our units, so it's kilojoule per mole. To get our energy units, multiply by moles. So that's all that happened there. Yeah.
What are those variables again? What's Q stand for?
Q is just heat, but really we're getting joules, right? So Q just means like how much heat.
Okay, so it's to be necessary to, okay.
Yeah, because you can talk about like energy and work. So that's the difference. Because when you're talking about energies of systems, you just want to distinguish between Q and W. But right now we're not doing work. All right, so try segment 3. Oh, so I'm trying not to reveal the answer. So how much heat is needed to heat up for leg 3? So taking our water now from 0 degrees Celsius to 100. And we're given these amounts. Our heat capacity, 4.18 joules per gram degrees Celsius. And take a quick bathroom trip. see if I need to recruit y'all for labor. All right, so what did we get for this answer? What do we get?
I got 8,640 joules. Oh, that was off.
Although some, right order of magnitude. So, double check the math.
Oh,
Typo.
yeah, I thought I put, in my calculator, I put 4.8 instead of 4.18.
Ah, that'll do it. Question?
Is the triangle T, is that the boiling point?
Delta T just means change in temperature. So it's just how much we're changing the temperature. Sorry, that was like kind of stupid sounding. But let's say, right, so for this question, our delta T was 100 because we are taking it right to the boiling point. But what if the question had asked, oh, how much does energy is needed to take it from 0 to 50? So then your delta T is 50. And so that's, you know, we were getting really excited about burning stuff to quantify it. But these are the equations, right, we would need to quantify it. So we could calculate the delta T in our water from, right, we burn whatever, the marshmallow, you quantify it, you look at that change in energy of the liquid, and then you can back calculate the joules that had to have taken. So then that's how you know how many calories were in your marshmallow or whatever.
So it's okay to leave it Celsius, you don't have to convert to Kelvin or anything?
Correct, and that's because they go up by the same amount. So it's for our purposes, right, it's kind of irrelevant because the change in temperature is the same for Kelvin and Celsius. But yeah, Fahrenheit obviously doesn't go up the same.
I'm sorry, last question, CS liquid, do you mind expanding a little bit more on that?
So all this is it's specifying the state. So this is heat capacity. So CS just means heat capacity, but then liquid means that it's in the liquid state. And that's where it gets a little overwhelming, like if you were to try to do this at home, because you got to look up, right, the heat capacity for the solid, liquid, gas of different elements. So that's why it's 4.18. And this is usually when people throw out the value of the specific heat of water. They always throw out this value, right? So you're in my oceanography class, so that's what we talk about when we're talking about the ocean, because we're looking at it in the liquid phase. And that's normally, of course, what water is on Earth.
And most of these problems we'll get like this, we'll usually have those conversions already done for us, or we'll have to do this.
So you would just have to plug in like the values. So, right, you would have to do this work.
Okay.
It's just typed out for us. But yeah, I would give you like the specific heat, so I wouldn't make you hunt it down. And then, right, read from the problem the mass. So of course, right, this is a moles to mass conversion problem. And then whatever the problem tells you with your delta T. All right, are we okay on segment 3? Yeah, and so right in our example, we're doing like the whole gamut, but any problem, right, we could stop at any point in the leg. We could have stopped at the melting point. We could stop at whatever degrees. So just watch out for that. All right, so now we're on leg 4. And it's now really seeing how much energy we need in this heat of vaporization. And so let's look at what we need to do. So again, our heat of vaporization, this would be something that's given to us. So 40.7 kilojoules per mole. We have 1 mole. And of course, the work is already done for us, but all we needed to do was plug those values in. And it's kind of trivial in this case since we're just doing 1, but that comes out to 40.7 kilojoules. Yeah.
Does that line on the graph stay stagnant until the entire mass has changed states? Okay.
Yeah, that's the idea. And, you know, I know in the real world, right, things start to get weird. Like, what if we just heat up one side of the ice cube and then half of it starts burning? But yeah, this is saying, right, we're going to take the whole mass, we're going to change it, and then we're going to heat it up. So that, yeah, trying to keep it all consistent. All right, so we feel okay about this. So again, heat of vaporization would be provided. We could look it up. Usually given in kilojoules per mole, but just watch those units. So then this brings us to segment 5, our last little bit. And so I'll make you guys do the calculation. And so again, notice we have a slightly different specific, or our heat capacity value. So now it's steam. And so now that we have made it to the gas phase, how much energy do we need to take that 100 degrees Celsius steam to 125? And so go ahead and plug that in, and we'll compare.
What does the T stand for again?
So that's our delta T. So right, we're going from 25 or 100 degrees Celsius to 125. So
So the difference between the two?
yep.
Okay.
And yeah, usually I just take the positive difference between them, and I only change the sign depending on the direction, right? So anytime you're adding heat, should be positive. Anytime you're going, right, condensing back down, that's where we would see negatives. So you don't confuse yourself. See, do we plug it in? What do we get?
Before sig figs, I got 904.5 joules.
904.5, I think that sounded good. So exactly, so that's what we got here. And 3 sig figs, so some rounding. And then, so the last little bit that this example problem didn't put is we want to probably add them all together. And so usually a question would be phrased in, so what is the total energy required to go from negative 25 degrees Celsius to positive 125 degrees Celsius for 1 mole of water. Right, so this could have been the question that was asked. So I could have given all this information on the side, right? The specific heats, the blah, blah, blah. And then you would have to go through this process. Oops, sorry, scrolled too much. So then you would have to break down that question into 5 processes. So does that make sense? So then to answer that question, we would just have to add up everything. So now let's add everything up, and we'll convert to kilojoules. Sorry, I can't find my calculator. There we go. So let's add everything up. So 0.941 plus, so again, adding in kilojoules, 0.602 plus 7.25 plus 40.7 plus 0.904. So then we get our final answer.
Why did you do it in kilojoules?
Uh,
You chose one?
yeah, so you could either do kilojoules or
One.
joules, yeah.
Okay.
It would be, come out to be 56.1, right?
Yeah, 56.1.
Because of the 40.7.
Yeah, so we're dictated, yeah, exactly, one after the decimal point. So that would be how you approach that problem. So again, can you take this question and then get this answer right, knowing that you have to break it down into some sort of curve like that? And you could be prepared to do this for any substance, and it would just depend, right? Identifying your melting point, identifying your boiling point, all those sorts of things.
Would you acknowledge plasma as a state of matter?
I mean, we can acknowledge it right now, but are we going to talk about it more than that? No, unfortunately. It's just so like extreme and rare, and high pressures, high temperatures. Like it's just not something we see.
You just came here to burn things.
Yeah. All right, I think we are finished for official lecture, but that being said, we could go over stuff. We could do more like mole practice. We could do more practice with this. We can quantify the CO2 like we were talking about. What are we feeling? What do we need practice on? We could do another heating curve. Do we feel okay about chapter 6 and 7 topics? We could get lab started early too. Looking for feedback. The main, so I'm a little behind on grading, I will admit. I handed quiz 3 back at least, so I'm a week off, but the main issue I noticed with that was just those diatomics coming back to haunt us. So that was a common theme for everybody. So I don't know if we want to do more practice of that, or if we feel better now. Still looking for feedback of what we would like to do. How are we feeling?
I still have a hard time with all the gas laws, like which formula, how you know when to use which formula.
I guess it depends. So I usually break it down, right? We have our PV equals nRT. And so this is used when we don't have like comparative conditions. And you kind of have to maybe write out your knowns and unknowns. But what I mean by comparative conditions is like with the other setup, so P1, V1, N1, T1, right, P2, V2. So these are like your 2 main formulas, I would say. But then to use this one, right, we have to have some sort of before and after pictures. We have to say, oh, the pressure started at this and was this, or the volume was this and then it was that. So there has to be some change so that we can compare. But if there's just like one of each, then we probably need PV equals nRT. So this is where you kind of start, is like which formula do I have enough information to plug into? And then you kind of have to go from there. And we could do the carbon dioxide problem as well. And there's different ways to do it. You can make it hard, you can make it easy.
I'm honest, I don't fully get chapter 7 even after reading it, but I think I'll go back to it and I'll
I-
problems again.
whether, I guess what was tricky about it, because chapter 7, like, half of it is these two formulas essentially, and then the other half is intermolecular forces.
It's, I think, the intermolecular molecular forces, like the, what was it called? Diatom? No, it was, oh, it was the dipole ones.
Yeah, so the dipole was just any time we have a polar molecule, we can say it has a dipole moment. So, right, thinking back to all the examples we've done, so looking back at some refreshers, right, we've said carbon tetrachloride, for instance, this is nonpolar. So then we expect it to just have van der Waals forces versus like chloroform or DCM. Right now I'm drawing chloroform, but right, chloroform then is polar. And so now this would have van der Waals still, but then also that dipole-dipole. So that's how you know it has dipole-dipole, is when it's polar. So anytime you see a polar molecule, dipole-dipole.
I'll write that down. So, but what about for like a London dispersion or a hydrogen bonding?
So remember, London dispersion, also known as van der Waals, so those are in every molecule. So every molecule has that. And then hydrogen bonding is just when it's hydrogen with oxygen, nitrogen, or fluorine.
So that'd be nonpolar or polar?
So a hydrogen bond is polar, but it's like a more extreme variation of polar, so that it's stronger, and that's why it's called hydrogen bonding, to distinguish it as being stronger than just a regular dipole-dipole.
Since London dispersion is weak, does that mean it's nonpolar?
It's not that it's nonpolar, it's just that, yes, the van der Waals are weak, so then these might have relatively low boiling points, right? Because there's not a lot of intermolecular forces to keep them together.
So they're all polar then?
They're not all polar. It's only, if they're polar, that means they have a dipole, but like, just like you did before where you identified polar versus nonpolar molecules, then you can tell.
Okay.
Did you want to do more gas law practice, or?
Sure.
So,
I know, I couldn't.
yeah, we could also look at the homework, but,
The homework. I tried doing it and I couldn't.
so which homework could you not?
Chapter 7.
So which one?
All of them.
What happened with number 1?
I wrote out all the things and then got stuck.
So let's just try number 1 then. So write out all the things, right? Write out your variables. And I don't like all these junk formulas. Huh?
The only one I like is that P equals NRP.
Yeah,
The rest, you just make yourself.
yeah. So N1, T1. So I prefer just looking at these two so then I can derive what I need.
Wait.
And so again, if you don't know what formula to use, just write out your knowns.
I did write out my notes and then I couldn't figure out which formula to use.
So we have, so walk me through your knowns.
Temperature is 298.
So 298, okay.
And the pressure is 0.759. And N is 3.25 moles.
And so we're
And
asked,
then V equals question mark. And then that's as far as I got. Oh crap, there's one more now.
are you talking about R technically? Yeah, so we have our R, so don't forget about
Top.
gas, yeah. I usually don't think about R, but you may need, if you need to highlight that, like, yeah, I do know R. So then that tells me, so this is what I was saying, right? There's no comparison conditions. We don't have any, like, final temperature and initial temperature and no final
Okay.
pressure.
So you use the ideal gas law.
Yeah, so we're stuck with this, and we can see, oh, we got temperature, we got pressure, we got moles.
So that would be the same with number 2 then.
Yes. And so let's at least plug in number 1. And make sure we are all on that same page. I'm just rewriting everything.
Is that 0.821?
Yeah, oh, sorry, I should have put 0.0. Yeah, I rounded, they took it out to more sig figs. Use whatever you feel comfortable. Will be slight discrepancies.
What would the units be? They'd be, volume?
Yeah, so what are so remember your units are dictated by your gas constant. So it's liters, ATMs, moles, Kelvin, so that means your volume is gonna be in liters. Because we're using this gas constant, we converted everything to ATM. We were in moles and we're in Kelvin. So what do we get for this one?
Oh, that one I got 105 liters.
So 105 liters. And that's our 3 sig figs. So is everybody okay with that one? So 2 we said was the same.
So 1 through 4 all go with ideal. 5 through 8 are competitive.
So then you want to look at 5 and see if you can. And I'll probably write our elongated formula. You still plugging it in. So we can at least go through and get kind of our simplified expression. So it says fixed quantity. So, oh, that tells me moles isn't changing, so don't have to worry about that. And, okay, so T1 to T2, I'll worry about that later. Looks like some volume, and it's heated at constant pressure, so get rid of that. So now I'm just looking at V1 over T1 is equal to V2 over T2. So I'll give people a few more minutes to plug that in. And as always, right, with these chemistry word problems, they pack a lot of information in there.
Huge cost multiplication, right?
Probably. Let's see, so now we can plug it in. What's 50 Celsius to Kelvin? Just help me for a sanity check.
Do we need to transfer it to?
50, it was 323 from 50.
So yes, we do have to convert it to Kelvin. So if you didn't do that, want to do that.
And how do we convert it to Kelvin again?
That's 273.
Add to, okay, that's what it is. Okay, thank you.
So yeah, we added 273. So I'm just going to start plugging it in. Remember, volume doesn't matter what it's in this case, as long as it's the same. So if we're in liters, we are going to get out liters. And it's now to start plugging stuff in. And so I think you were correct. We got to do some cross multiplication. So 3.75 times 323 divided by. And you can also, right, before you punch everything into the calculator, kind of do a sanity check with yourself. Do I expect my answer to be higher, lower? And so we're taking gas and we're heating it at a constant pressure. So we're already thinking, I'm probably going to need to expand this volume so that my pressure is held constant. And so that's what I get with the math. Verifies our sanity check. So do we all get this answer? 4.06. Yeah, small discrepancies with rounding, as long as you're somewhere clear here, somewhere around 4.1 liter.
And that's liters.
Yes, because we were in liters here. So this one is just the units are consistent with itself. Okay, what other one? Should we do one more? Okay, let's try this one, number 7. So we don't often see mole changes. So we have a 1.25 mole sample of gas occupies 25 liters at a certain temperature and pressure. So what will 2.25 moles occupy then?
because it says constant at the same temperature and pressure, so we're leaving temperature and pressure is constant, so we use avocado.
Exactly. Yeah, so just, again, guesstimating, probably imagine we're almost like doubling the moles. We'll probably have to almost double the volume or something like that. And then what do you get when you all punch it in? So 45 liters, so again, for my mental math, that sounds pretty good. I see nods, so I think there's consensus. We're still plugging it in, it's fine. All right, any other last questions on this one or other topics?
Well, so we don't add in the avocados there? How do we change it from moles?
You just leave it in moles, because even though it's like the Avogadro's relationship with the gas laws, we don't need to put in, the Avogadro's number, because it wasn't, the question itself didn't ask for like individual molecules or atoms. So that's when you know to use the 6.022, and it's either asking you to convert, right, individual molecules or atoms, or find how many. Any other last questions? Hmm?
I said our forever hold your peace.
Yeah. It's like, silence is golden, except right now. Yeah.
I object. Or whatever that phrase is.
I object.